In the previous video, we have seen the Fisher projection for the cyclic structure of fructose. Now here we are going to see the Haworth projection for the cyclic structure of fructose. See, Haworth projection can be written in two ways. One is pyranose structure and second one is furanose structure. In pyranose structure, fructose is found to have 6-membered ring. And in furanose structure, it is found to have 5-membered ring-like structure. Pyranose structure resembles like pyran, which can be represented as this or this. This you have seen in the structure of glucose as well. So this is not going to be a problem for you. So to write pyranose structure, we'll take help of the Fisher projection. See, here this is beta D and this is alpha D form of the Fisher projection cyclic structure. I have written the number of the carbons. So oxygen you can see here, followed by first carbon, second carbon, third carbon, fourth carbon, fifth carbon, sixth carbon. So now look at here. First carbon, oxygen, ring starts, then cyclic means clockwise. Second carbon, third carbon, fourth carbon, fifth carbon and sixth carbon. You can see it here. Here we have first carbon, then we have second carbon, third carbon, fourth carbon, fifth carbon and sixth carbon and this O here. So here we have got 6-membered ring-like structure. Since in this structure OH as per the Fisher projection follows on the right hand side of the second carbon, same way in the pyranose form, OH is as per the Fisher projection. So this configuration is alpha. D stands for the configuration of OH with respect to fifth carbon. So you can see here fifth carbon OH on the right hand side. Minus stands for its levorotatory nature. And we are not writing fructose here, we are writing fructopyranose. What is the meaning of fructopyranose? Fructose exhibiting 6-membered ring structure. So for this reason we are calling it fructopyranose. Now we'll see the beta configuration. Beta configuration. Now in the beta configuration on the second carbon OH is on the left hand side. So when we write it in terms of pyranose form, so it appears like this. Here we have first carbon CH2OH, then we have second carbon where OH is on the left hand side, then third, fourth, fifth carbon has no change as in alpha, same R and beta. Then we have sixth carbon HH. Here point to be noted, sixth carbon is CH2. So CH2 here, C single bond H, single bond H, C single bond H, single bond H. So here it is beta D minus fructopyranose. Beta is the configuration with respect to the anomeric carbon OH on the left hand side. D stands for its configuration of OH on the fifth carbon. Minus is optical rotation, levorotatory nature and fructopyranose. Now we need to understand furanose structure. In the furanose form, fructose has got 5-membered ring where it resembles furan. Furan is represented that way. This compound is furan. Alright. So in the furanose form, here it is represented in these two forms, alpha D minus fructofuranose and beta D minus fructofuranose. In order to understand these two structure, let's see once again the hemiketal formation. In case of furanose form, the hemiketal formation takes place between second and fifth carbon. For the pyranose form, the hemiketal formation takes place for second and sixth carbon. In furanose form, the hemiketal formation takes place between second and fifth carbon. I hope it is clear to all of you. Rest all things are very, very clear to you. So on hemiketal formation, you have this kind of a structure which will be formed here. CH2OH, second carbon CH2OH bonded with CH2OH, OH. Then third carbon resembling this, fourth carbon resembling this. Now fifth carbon will have one side CH2OH, where this will be your sixth carbon, and H. Now this is the Fischer projection for the cyclic structure of the furanose form of fructose. And or we can have this configuration as well, since second carbon is the anomeric carbon. In this structure, OH is falling on the right hand side, so this is alpha D minus fructofuranose. Now fructofuranose can be represented in this way also, where anomeric carbon, that is second carbon, has OH on the left hand side. Rest all things are same without any difference. Now if we write Haworth structure of these Fischer projections of the fructofuranose forms, then Haworth structures will appear in this way. Let's see for beta first. O, clear? Now first carbon, which is as CH2OH, so first carbon CH2OH. Since in the beta CH2OH is on the right hand side, so it is coming down now. Then OH, then third carbon, fourth carbon, fifth carbon, and sixth carbon CH2OH. Only you have to rotate the structure clockwise. So when you are making this furan form, then these groups you have to rotate clockwise. All the groups which are on the left hand side, they'll come on the top, and the groups on the right hand side, they'll come down. So you can see here CH2OH, OH on the second carbon, OH, CH2OH, OHH, OHH, HOH, HOH. Then we have on the fifth carbon CH2OH, H, CH2OH, H. So this is beta D minus fructofuranose, Haworth projection. Now for alpha D minus fructofuranose, the Haworth projection will appear like this. Only the difference will be on the anomeric carbon, rest no difference. For the anomeric carbon, OH is on the right hand side, CH2OH on the left hand side. So CH2OH is coming up, OH is coming down. Rest all things are same. So this is Haworth structure for alpha D minus fructofuranose.